Well, hello and welcome to the last seminar for ITS Berkeley. Today we have Stephen Wong and Yulin Liu presenting their graduate work. Here to introduce our first speaker is Mark Hansen.
Hi everyone, can you hear me okay? Can someone hear me okay? Yulin, can you hear me?
I can hear you.
Yep, I can hear you okay.
All right. Yes, thanks to everyone for attending this seminar and hearing about the thesis work of two of our finest graduate students. So the one I'll be introducing is Yulin Liu, who I first met in Beijing in, what, 5 years ago now? Something like that. And I think we, the first thing we did was tour the Forbidden City. And then looked at Tiananmen Square and many other sites around Beijing. Since then, we have done many other forbidden things. We have worked on a lot of different research projects together. And when I say we, that's somewhat of an exaggeration of my role. But it's been great to watch Yulin's development and increasingly large repertoire of technical skills and domain knowledge in many aspects of aviation. He's published papers in everything from flight operations to network modeling to airport slot pricing and allocation. So he's had a truly diverse research experience here. And it's been a great honor for me to work with him over the years and to supervise his thesis, which he will now be presenting parts of.
Thank you, Mark, for the nice thing you talked about me. I truly appreciate it. So I think I'm just go ahead and share my screen, if that's okay with everyone. And I'm going to turn off my video. Is that also okay for everyone? Can everyone see my screen? Can you see my screen, Mark?
So, yes, I can.
Hello, everyone. I'm Yulin Liu. Welcome to the seminar. Thank you, everyone, for joining us. And today I'm going to present my thesis work, Trajectory Modeling in the National Airspace System. So a little background about this thesis. In recent years, we have seen an emerging demand for performance analysis in the NAS that include identifying key performance indicators, define metrics, assess trends, and discover patterns. So for example, in the NAS, usually people divide it into different segments. For example, we have terminal airspace that include departure airspace and arrival terminal airspace. And also we have the en route airspace. In each of these airspace, we typically define multiple metrics to assess their performance. So for example, in the departure airspace, we have taxi out efficiency to evaluate how efficient the taxi out performance is. And in en route airspace, we have en route inefficiency, which we'll talk mainly in a few minutes later, that try to assess what's the distance traveled of the aircraft is respect to some benchmark distance. So among these different metrics, the en route performance in mass has been gaining more and more attention in recent years, mainly because it is core to aviation economics, and also it has significant impact on the environment, due to fuel and emissions. And also joined by FAA and Eurocontrol, they have defined a metric called horizontal en route inefficiency, or HIE. So to be a little bit more specific about this metric, HIE, here we have, we have a flight departing from the departure airport to the arrival airport, and then we draw a 40 nautical mile circle around the departure airport and a 100 nautical mile circle around the arrival airport. And then we calculate the two distances. One is an actual distance, or A, from the exit point to the arrival, to the entry points. And also another distance, which we call H, or achieved distance. It is a benchmark that is proportional to the grid circle distance from the departure airport to the arrival airport, but has somehow accounted for the location of the exit and entry point of here and there. So we can think of it as the projection of the most direct route from the exit point to the entry point on the most direct grid circle trajectory. And then basically we can use the following equations to calculate the HIE. So it's in a percentage perspective. So there are a few sources of en route inefficiency that has been detailed graphed in this figure. So after leaving the departure fix and before before entering the arrival fix, here corresponds to the en route airspace. And some sources can be restricted airspace, congested airspace, adverse weather, traffic management initiatives, and something that's special to Europe, expensive airspace. So these different sources can be particularly influential to the en route inefficiency. So in the US, there are a few initiatives to improve the en route performance that include traffic flow management initiatives, or TFMIs, that try to apportion air traffic into a management flow. And in particular, these TFMIs include miles in trial restrictions and airspace flow programs. On the other hand, in the US, we also have National Route Program, which tries to design the route structure in national airspace. However, it preserves a lot of constraints on flight route and planning. Among these initiatives, there are a lot of questions or concerns about whether they are necessary, and if they are necessary, what are their impact? So these concerns the questions, I think, for our research. So after obtaining a big data set from the FAA containing about 6 million flight records from and to the 34 core US airports in 2013 and 14, we are able to calculate the HIE for each flight in our data set. And then we can summarize them into this bar chart. So we first look at the average inefficiency in 2013 and 2014, and we see they are pretty comparable with an average value of about 3.4%. But if we categorize them into different grid circle distance categories, we basically can see short haul flights like here, 0 to 200 nautical mile class, are more inefficient than the long haul flight, for example, for flights that is greater than 1,000 nautical miles. So we can further group the HIE by airport pairs and month. So for example, here we show a comparison between two airport pairs. One is from Minneapolis to Miami. Another one is from Minneapolis to LAX. Both two pairs have relatively similar grid circle distance, but they have a pretty different distribution of HIE in terms of different months. But the bottom line here is we do observe that inefficiency for summer seasons, for example, May, June, July, and August, are higher than the other seasons, and also they have larger variance. And we have also two more pairs to compare. They are from Atlanta to New York, and also Atlanta to JFK. Both New York and JFK are in the New York Metroplex. They are very close to each other. However, we see from this box plot, they have very different inefficiency metrics. So upon here, naturally, we're trying to ask, why is HIE systematically higher in summer seasons? Why does HIE vary drastically across airport pairs? And what can we do to improve the en route inefficiency? So answers to these questions leads to our research goal. So we're trying to identify factors that induce inefficient en route performance. For identified factors, we want to estimate their contributions to the HIE. And to be a little bit more specific here, in this study, we have identified the following 5 factors: convective weather, the wind, miles and travel restrictions, airspace flow programs, special activity airspace. These factors are mainly from the literature and also from our practitioners in the industry. So before we jump into the modeling philosophy and the modeling techniques, I would like to introduce our data sources and some of the aviation acronyms and terminologies. So the first data sets we have is a 40 trajectory data set. It include latitude, longitude, altitude, and time. And then we have 3 different weather-related data sets that include the ground-based weather station convective weather. So each dot here corresponds to 1 ground weather station. And then they are trying to report whether or not there's going to be a thunderstorm, rain, or other weather phenomena. We have a forecast wind data that describe the wind direction and the wind speed. So these 2 data sets come from NOAA. And lastly, we have another more high fidelity national convective weather data. So that includes the location of the convective weather polygons with their altitude and speed information. So if you plot the polygons on a 2D plane, then it looks something like this. And then we have our 2 TMI data sets. So they're from the National Traffic Management Log, which include where, when, and how these initiatives were implemented. So the first one is the miles in trail data set. So a little knowledge here, an MIT restriction enforces a minimal spacing or a number of miles between consecutive aircraft. So flight subject to MIT will either slow down or take maneuvers to satisfy the spacing requirements. So for example, here, the Salt Lake City Center here in green polygon is maybe having some capacity issue. So the Denver Center issue at MIT that will be enforced as NASA element ONL here. So flights that go across these 3 facilities will be enforced by an MIT restriction. The AFP, or Airspace Flow Programs, on the other hand, identifies flow constraint area, or FCAs, and assign to delays to a flight that flies into those areas. So the FCA can be a line like this, or can be a polygon. So flights subject to AFP will either delay their departure times or choose another route to go around FCAs. So as you can see, for both of these 2 TMIs, flights will either take maneuvers, extending routes, or go around FCAs. So they can extend their routes by increasing the en route inefficiency. So lastly, we have our special activity airspace data sets come from the NASA Sherlock Data Warehouse, which include the time of activation or deactivation of each SAA. So there are a few common SAAs that include alert area, military operations area, etc. But the bottom line here is flights almost always go around SAAs, except for warning areas, because warning areas is along the coast area, and they are not really enforcing flights to go around them. So after obtaining the data sets, here enters our modeling philosophy and techniques. We're trying to link those factors directly or indirectly to the HIE. So how are we going to do that? We here propose 2 types of mechanisms. The first one is strategic route choice. Basically, before a flight departs, we are trying to mimic the process where the flight needs to choose from route 1, route 2, etc. And those different routes are inherently different with respect to HIE. And then the second mechanism followed followed is called a tactical reroute. So basically, after you choose to fly one route, you may be subject to many maneuvers or extending routes or vectoring just to adapt to some certain situations, such as weather and TMIs. So flight using the same route might have a varying level of inefficiencies. To be a little bit more specific, our modeling philosophy contains two separate models. The first one is the route choice model, whereby we try to construct a scenario, a flight where prior to its departure, it's a decision maker that needs to choose for a wide alternative route, because the utility is going to be a function of attributes derived from these identified factors. And the underlying techniques include the first step, constructing route choice set by trajectory clustering algorithm and attribute identification via some tree-based matching algorithms, and lastly, statistical modeling via the Login models. For the inefficiency model, we're trying to predict our inefficiency. Had we known which route a flight is going to fly and attributes of that route. So the underlying techniques contain a linear model and counterfactual analysis. So here is our detailed methodological framework. So first things first, we need to construct a choice set. So a choice set is defined as a small representative set that has high intra-set similarity and a low inter-set similarity. So all these properties reminds us of popular techniques in data mining called clustering. So here we can do something called trajectory clustering algorithms. So basically here we have adopted a very easy, simple, but very efficient algorithms. It's basically a four-step procedure. We first do trajectory resampling to make the each trajectory equal length. And then we do PC analysis to reduce dimensionalities. And then we do DB scan clustering to actually form clusters. And then we do try to solve a 1 million problem to obtain something we call a nominal route or the route alternatives. So here we show two examples of our clustering results. So the first one is from Houston here to Boston here. So basically, we have formed 5 natural clusters: the red, cyan, magenta, blue, and green. And also we have some black curves or black trajectories that are classified as outliers, which does not belong to any natural clusters. So here we have 3 dominant flow: red, magenta, and green. Each of them has roughly about 30% of traffic. And the magenta is one of the most efficient dominant flows. So we have another example showing here for flights from JFK in New York area to Fort Lauderdale in Miami area. So basically, we have 5 natural clusters, but only have 1 dominant flow, which is the most direct route, as in red. And also we have 1 alternative flow here in green, which is the minority, but it goes around a lot of TMI area, as will be stated a little bit later. So we have applied this to, in this study, we have applied it to another 6 pairs. Those include from Boston to Houston, Fort Lauderdale to JFK, San Francisco to Orlando, LA to Cleveland, New York to Las Vegas, and San Francisco to Minneapolis. So after we form the choice set or a nominal routes, the next thing we want to do is to, in terms of the route choice modeling process, we want to identify the attributes for different alternatives. So here we call it an attribute identification process, which actually include 3 steps. So in here, we have a very tedious and complex tree construction batch 4D matching process, which we don't really have the time to go through. But I would like to emphasize a little bit about the synthetic 4D nominal route process, since it is most subtle in this research. So basically, as I stated a little earlier, this route choice process is trying to mimic the scenario where flights needs to choose a route from a choice set obtained from the clustering results. So essentially, we're asking the question, for a given flight and for each of the nominal routes, what would likely have happened to that flight with respect to weather, wind, TMIs, and SAAs if it had used that route with its original departure time? So this is the question we want to answer. And here is our procedure. So for flight I, we extract its departure time Ti, and then we are mimicking that it's trying to choose from one of these nominal route, 1, 2, all the way to n. So that we need to replace the timestamp, especially the departure time of each of the nominal routes 1, 2, all the way to n with Ti, and also replace the subsequent timestamp of each of the nominal route. So after this replacement, we construct nominal route 1 prime, 2 prime, all the way to n prime. And then we do 4D matching or true-based matching for those nominal routes 1 prime all the way to n prime with convective weather data, wind data, TMI data, and SAA data to calculate their final attributes. So our tree-based matching algorithm is pretty complicated and tedious, so I'm not really going to go through them. But the underlying technique there is KD tree and nearest neighbor search. Here is the summary of our attributes. So for weather-related variables, we have thunderstorm exposure, and we have ground-based weather exposure variables, including rain, score, hail, etc. All these variables are in the percentage value, and the higher the value, the larger the exposure to the route or the alternative. And then for the wind, we have the axis distance traveled in the steer air. So the larger magnitude indicates higher tailwind, which is typically favored by flight operators. And then we have MIT, AFP, and SAAs. All of them have their identified metrics to evaluate how their impact to the route. So for the statistical modeling, we have 2 different models associated with our 2 different mechanisms. For the first one, the route choice model basically answers the question of how would different factors affect the utility of a route. And the inefficiency model answers the question of, given the route choice probabilities, how would different factors directly affect the HIE? So let's talk about the route choice model. So basically, it's a logit model, and whether it's a multinomial logit or nested logit, that depends on the OD pairs and our experimental trials. So in the specification, each of the utility contains the alternative specific constant, some generic attributes linked to departure time, and also we have a list of alternative specific attributes with weather, wind, and etc. And here is our estimation result. So first of all, we look at the nesting coefficient. So after trial and error and the log likelihood ratio test, we only see that 2 pairs among 8 have a nesting effects. That is the Houston to Boston case, where we have 2 non-degenerate nests. And another one is from JFK to Fort Lauderdale, that only have 1 non-degenerate nest. Then we look at the estimates of the weather-related variable that contains convective thunderstorm and the rain. Only these 2 report significant estimates. The thunderstorm have all negative estimates and significant estimates across all the pairs. And that concludes that flights avoid convection almost all the time. And then for the wind estimates, we do see large positive estimates for 6 pairs. 4 of them are long-haul transcontinental flights. So that concludes that flights always chase the wind. Notice that for these 2 pairs, JFK to Fort Lauderdale or Fort Lauderdale to JFK, we don't see significant estimates because these 2 pairs are north to south or south to north operations. So basically, flights in that direction will barely be affected by the wind. And lastly, we see estimates for TMIs or SAAs. Basically, they are not really significant for all the pairs, but for those identified pairs, flights do dodge those TMIs. So with the inefficiency model, this is basically a linear model with a dependent variable as the HIE and the independent variable, including everything in the logic model and a cluster fixed effect CJ. And then we plot the data sets for the 8 pairs, and then we estimate the model. R square ranges from 0.26 to 86%. Thunderstorm exposure is highly significant for all 5 pairs. And MIT, AFP, and SAS are significant only for certain airport pairs. Also, we noticed that estimates of cluster fixed effect are highly significant. Here in the box, indicating the substantial between cluster effect. We also see the order of these estimates match the statistic we have for the cluster results. And then we also observe that the summer season fixed effect, as we see here, are not really consistently larger than the others, which seems to be a little surprising when we think about those box plots that summer season typically have larger inefficiency. However, this is explained by that convective weather activity has been explicitly accounted for in one of the variables here, thunderstorm. So that absorbs much of the effects for the summer season fixed estimates. So after we obtain these estimates, we want to estimate estimate the contributions of different factors. So here we use a technique called counterfactual analysis. Basically, we compare the base case with counterfactual case, where the base case uses the original data set, and the counterfactual case set the factor attribute to 0, or we try to clear the sky in the airspace. So here we can estimate the expected inefficiency by, under the base case and under the counterfactual case. And then we calculate the percentage change of the inefficiency, and use that number as the estimates for contribution for the contribution of factors. So here comes our results. So we first see that we do only see a moderate weather contributions. So that corresponds to most of the transcontinental airport pairs. And also we see strong wind impact, especially for long-haul transcontinental flights, as listed here. For TMIs, that's a little different. We only see like large contribution or moderate contribution for far latitude JFK. That is because we have a very popular FCAs here in the middle of the airspace. And also we see that this FCA is typically almost all the traffic from JFK to Fort Lauderdale will go across. So sometimes they just choose to fly to this route to go around it. And also we see some big contributions for flights that's coming out of the southwest area, because this area airports are typically covered by active military operations areas. So after this, we have estimated contributing different factors. We have done some overall assessment. So another question is, how can we really improve it? Well, where the future of the NAS is. And then in FAA recently, they have another program called TBO, or Trajectory-Based Operation Vision 2025. Basically, in this one, they're trying to use the 40 trajectories to both strategically manage and technically control the surface and airborne operations. And the core to this TBO is some tool to prediction. So essentially, we're trying to ask where the flight is going to be at a time of interest. And this question leads to the second part of the thesis, where we try to develop trajectory prediction tools that can incorporate flight plan information and also incorporate uncertainties such as adverse weather and wind. And also we can predict the flight tracks given some initial conditions. And the nature of this problem is a sequence-to-sequence prediction. So since we don't really have enough time to go through everything, I'm going to just overview the approach. So in this one, we propose a deep generative model that the inputs are related to the convective weather, wind, and temperature in the vicinity of the aircraft and the flight plan information. And the outputs are related to the flight coordinates modeled as Gaussian mixture. And the feature engineering is basically a revision of the previous feature engineering in the root choice model, but we modified it to enable batch model matching during the training and recursive matching during the inference. So I'm going to talk a little bit about feature engineering, because here we are not really just to do a point match. On the other hand, we are trying to construct some feature cubes that's in front of that's in the vicinity of the aircraft. So basically, for each track point, the feature cube contains 4 layers of information: convective weather, temperature, westerly wind speed, and southerly wind speed. And each of these layers contains an image about 20, with dimension of 20 by 20. So you can think of this cube as a 4-channel colored image. And then after we obtain this, we propose a end-to-end encoder decoder LSTM network. Basically, the encoder inputs the flight plan information, and decoder learns the spatial temporal correlation of the flight tracks. And then we have a convolutional layers to learn the feature representations of the feature cubes. The y variable here is the parameter set of the Gaussian mixture. The loss function is constituted by the log likelihood function. So after we do the training, we can do the inference. So here, the inference procedure is a little different, unconventional, or it's not really just a feed forward, because the vanilla inference procedure will typically produce a high variance and non-smooth samples. So to tackle the issue, we have embedded actually 3 different modules. One is called adaptive common filter here, and also another one is called RTS smoother. So these 2 modules try to prune the variance or covariance matrix of if we don't use beam search, the Gaussian mixture components will sample exponentially grow number of track points. And then we have our in 20 small compared to most of the state-of-art method of the horizontal arrow about 50 vertical arrow. And here shows our 2 So now I would like to end my presentation by found that whether wind, TMIs, and SAs have significant here's a picture of us in Beijing, and also I'd like to thank our committee member, Dr. Cassidy, Dr. Peng Ding, Dr. John Walker, and also our colleague in Maryland, Dr. Michael Ball, and Dr. David Lover. Thank you all for screen share. Stephen, is that right?
Yes.
Yeah.
And
All right.
this is Susan, Stephen.
Hi, Susan.
Hi. Surprise.
Not expecting that,
I'm-
but Lovely.
Yes,
Thank you.
I'm Zoom bombing you. I hope you will entertain my Zoom bomb for a moment. So I'm here to introduce Stephen on behalf of me and myself and Professor Walker. We're Stephen's co-advisors, and we're so delighted to see him presenting today. We've been working with him for quite some time. I first met Stephen back in 2016 in my class, and I imagine that Professor Walker also met him around the same time. And he approached us both to mentor him and work with him on this topic of evacuation challenges. And we came together to put together this work, which Stephen's going to present today. I wanted to just provide you with a few highlights on his background. It's very impressive. So as many of you know, Stephen is a doctoral candidate and is hoping to wrap up this spring. He has a Bachelor's of Science degree in Civil and Environmental Engineering, and also a joint degree alongside that in Sociology from Johns Hopkins. He completed his MS in CEE in 2016. And we've been working really hard on this focus of evacuation behavior and really looking at whether or not there was an opportunity to leverage the sharing economy to provide both mobility and sharing resources to support disaster response and relief. And so Stephen has received many awards along the way, including National Science Foundation support, the Dwight Eisenhower Graduate Research Fellowship. He's also received support. He participated in their leadership program. He's currently a graduate student researcher with me on the California Resilient and Innovative Mobility Initiative on behalf of UCI. And he's also a member and leader in TRB and participates in the business my own right.
Continuity.
I just welcome you to share your dissertation with everyone and just let you know how proud we
Matt, so all right, so today I'm going to be presenting on critical evacuation challenges at minimization, Susan Jean and Joan Walker. So just a brief outline, I will be working through first very briefly through the context and then go through critical evacuation challenges, followed by innovative opportunities, which is really my contributions to the field, and finish off with some of the key results and conclusions we got from this. So first, the context, I'll do this very briefly. This is a evacuate wildfire ordered it has these a couple years ago, as well as a company. Oh, all right. Behind all this is intensity and frequency of rainfall, heat waves, and wildfire development, and populations in high-risk areas. Both of these are combining such that these evacuations are not only becoming larger, but they're becoming in crisis, these evacuations at the same time as the pandemic. So from the start, one of the biggest issues is compliance. Compliance is related to the complete evacuation from a hazardous area that has been issued a mandatory evacuation order. The problem behind here, though, is that there's persistent non-compliance. So compliance rates for hurricane evacuations range from 34% to 69%. Thankfully for wildfires, it's a little higher, from 87% to 97%. Of course, compliance is a function of many things. It's first just a function of choice. Some people don't want to leave. They don't want to go anywhere. They think that their home is protected and that they are safe. Some are not physically able to evacuate, especially a lot of older adults and individuals with disabilities. And then there's also a resource constraint. Individuals who do not own vehicles, do not have enough assets or emergency funds, or don't know of a place to shelter, also tend to not want to evacuate. For wildfires, there's one more unique defending behavior that is related to protecting property. People will stay behind to protect their property, and that causes additional challenges that I won't necessarily address here, but it's just something to note. Next is the next challenge I wanted to address was congestion, and related to that is transportation response. So heavy congestion is a growing problem in the evacuation field. This was actually not much of an issue before these large scale and the wildfires. We also saw major congestion, and the traffic was moving so slowly compared to the and actually run, which is a critical problem here in this work. And the question becomes, where and when should we use transportation resources, such as phased evacuations, Counterflow, which is switching all lanes to flow out, shoulder usage, route closures, public transit. There's a lot of different transportation responses that we can use, but the question is when and where should we use it? The last critical challenge that I wanted to address was social equity. And there's in shelter. And when I talk about social equity, it's really about preventing and reducing inequality, unfairness, and injustice. And we saw it most acute during Hurricane Katrina in 2000, severely impacted careless, low-income, and African-American residents in the city. And we've seen that in subsequent hurricanes that these problems are persistent. Recent research has found that only 20% of evacuation plans of the vulnerable individuals. So this is a pervasive challenge, as well as the fact that 77% of those who perished in the Camp Fire were over the age of 65. So this is having really bad consequences for those most vulnerable, and the evacuation process is a critical component of all of this. So now that I've talked about the critical evacuation challenges, I want to jump into the innovative opportunities that I see in order to address these three challenges. The first one, which Susan alluded to, is the sharing economy, and really trying to understand what is the feasibility of the sharing economy and emerging mobility in evacuations. We've seen a growth of new technological connections. Smartphone adoption continues to climb. The sharing economy platforms such as Airbnb, Uber, and Lyft also now exist. And the problem is that there's been really minimal exploration in the role of the sharing economy in disasters. Since I presented my first paper back in 2018 at TRB, there's only been a little bit of work. And so we're starting to see the ball rolling, but there's a lot more that needs to be addressed here. And the idea behind the sharing economy is that resources from private companies or citizens could supplement public resources. So to add to the literature and make contributions, I set out and did 4 specific things in my dissertation. And this is, I just want to provide just a brief side note that this is all an aperitif, as I like to say, of what I'm doing in my dissertation, a really high-level overview. So I'm not going to go specifically into the modeling, but I want to give a high-level kind of view of what I did. So for the sharing economy contributions, I looked at the current state of the sharing economy in evacuations. the benefits and limitations, as well as willingness of private citizens to provide their own resources. These resources don't have to come from a company. They can come as a business-to-peer model. It can come from a peer-to-peer model. Next, I want to know to understand the impacts of the different factors on the willingness to share either transportation or sheltering in a disaster. The reason why I want the sheltering aspect is because these two aspects are very closely aligned with each other. As I noted way back before, the shelter aspect may be why some people decide not to evacuate if they don't have access to shelter. Next is the extent to which shared resources can either benefit or limit social equity for vulnerable populations in evacuations. I wanted to really look at that lens. And then finally is the behavioral nuances of different models. And this is where I go into a little bit the more technical side, looking at latent classification and potential joint modeling of individuals to share. And what this means is if I'm willing to share transportation, am I also willing to share sheltering in a disaster? This is just a brief list of the publications. You can feel free to look those up, but this is what those contributions are based off of. The next innovative opportunity I wanted to look at was, in parentheses, joint choice modeling. It's not just all joint choice modeling, but that's the emphasis here. And that's the implications of evacuation choice making. Individuals have to make a series of complex decisions beyond the decision to evacuate. You have departure time, route, destination, transportation mode, shelter type, even reentry timing. And all these different choices eventually impact the transportation system. And agencies have, again, a series of transportation responses to address the congestion and traffic and issues related to it. Except there's a lot of gaps with little or no work on a number of different areas. First, wildfire choice making. Most of the work is in hurricanes. And so wildfire choice making is very understudied, as well as just other transportation choices like mode or shelter type or destination. Along with this is unobserved classes of people and attributes of alternatives. In the evacuation field, most of the discrete choice modeling focuses on demographic variables and risk perceptions, not necessarily attributes of the alternative. And then finally, the emphasis here that I want to make in my dissertation was a multidimensional decision making. Rather than saying that there should be a separate model for departure timing, a separate model for route choice, what if we start combining them together and seeing if there's any correlation among these different choices that can help us with a more nuanced strategy. So my contributions here is I look at the joint preferences of sharing on multiple different transportation sheltering scenarios. I also conduct the latent classification of individuals for evacuator stay and actually find two different distinct classes there. I'll go over that briefly. And then the real contribution here is the decision dimensional dependency of choices, both for hurricanes and for wildfires. And I use a portfolio choice model, which is able to capture this dimensional dependency in a relatively parsimonious way, which is very beneficial in terms of modeling, but it also allows us to look at the structure and just look at the correlation if there's joint preferences or joint dislikes for these different dimensions. And finally, I did an attribute-based assessment of wildfire evacuation choices beyond the decision to evacuate or stay, which has not been done in the literature. So a lot of this is trying to plug these gaps that exist all over this field. So if anyone is interested in getting a dissertation in this topic, please let me know because there is still much more to do. And these are the publications on that. The last area innovative opportunity I want to go over is regret minimization. And so in all these discrete choice models that I've talked about beforehand, I've assumed that people are maximizing their utility or satisfaction. And so in a disaster situation, people may not be maximizing their utility. They may be thinking more about regret. And regret is experienced in difficult and important decisions when feedback is very rapid on the choice. So there's some level of accountability. And so the hypothesis here is that regret minimization may better explain a behavior in an evacuation choice context. And so this random regret minimization RRM model has been developed before for transportation by Kasper Koris at TU Delft. but it still requires more exploration in evacuations. There's been 2 studies so far on using stated preference data. The problem is that it's hypothetical, and we're not actually using the real choices of an individual in an evacuation. And so I wanted to go through and look at it in a revealed preference standpoint, which is my contribution to the field here, is analyzing the regret minimizing behavior and developing a specific RP methodology for challenging choice sets. So those are all the innovative opportunities and contributions. How do I do all this? A lot of surveys. Turns out surveys are very difficult to do post-disaster. People are hard to find, and they have many other more pressing matters to do, to go through than to fill out a survey, specifically recovery from the disaster. So this was a challenge, but these are empirical contributions. To my knowledge, these are the only post-disaster surveys for these 3 disasters that exist in the literature. And so this represents a really important empirical contribution, as well as I realized that a lot of these surveys, because they were online, didn't capture vulnerable group choice making. So I also conducted 4 post-disaster focus groups of individuals impacted by California wildfires, low-income, older adult, individuals with disabilities, and Spanish speaking. And I also conducted some expert interviews on my foundational paper to understand expert opinions related to evacuations. So the intersection of all these challenges and dissertation research topics is here. I wish I could fill out all the boxes. Unfortunately, that was not the case, but I tried my best. Some of these will require further research and improved data, but you can see how all these different areas are intersecting with each other. So now I'm going to go into the results and conclusions. These are going to be some very high-level results. I'm not going to go into modeling details or anything too specific. I just want to give a broad overview. I want to first present some of the results that are important, but I'm not going to go into a little bit more detail on. These are just general ones. And the first one is I found that sharing economy companies have acted in disasters since Hurricane Sandy in 2012. In fact, they've actually acted in over 30 disasters since 2012, and they will continue to act. What's interesting is that these companies have improved their actions and have made it more structured, and we're seeing this now as they respond to COVID-19. So this kind of carries on that policy making at the company level. Next is there are significant limitations, however, that need to be overcome to build a sharing economy strategy. They include reliability, they include the matching mechanism. Trying to find low-tech solutions and communication methods in a disaster is a huge limitation that still needs to be overcome. And there are still a substantial social equity barriers related to the sharing economy, such as vehicle accessibility, or the ability of drivers and hosts who are trained to assist people to a vehicle or assist people in terms of even providing to some level medical care. And so these limitations, I do want to preface all my sharing economy results by saying that this is still really not yet feasible in terms of a broader strategy if we don't address these limitations. Next is the selection of the discrete choice model to switch gears really changes the influences on the factors on willingness to share resources. And this was an interesting result that we came out of. We tried all these different models. We're trying to see, and it was kind of a storyline. We first tried basic binary logit models, transitioned into a joint choice model, and then into latent class. And what's interesting is that through that thread, people's willingness, the factors that influenced willingness changed throughout that. And so the note there is be cautious of what model you choose because it can really influence your results. Next is I found that there are 2 classes of individuals for hurricane evacuations, evacuation keen and evacuation reluctant, that respond differently to mandatory evacuation orders. The evacuation keen group will evacuate pretty much regardless of if you give them evacuation or not. They are gone and they do not want to deal with the hazard. The evacuation reluctant group, though, however, once you give them a mandatory evacuation order, they are more likely to evacuate. And so there's different compositions of those classes, which I can talk about perhaps another time, but I just wanted to to provide that note. And finally, attributes matter for some wildfire choices, but not all. And so this is going back to the difference between attributes of alternatives or demographics or risk perceptions. Attributes really matter for route choice and departure time, but not really for mode choice and shelter type, which makes sense. It's most likely a function of availability of those resources and perhaps more demographic variables. So those are a couple of a little aperitif of some of the results I've gotten from my dissertation. However, I want to dive into a couple really unique results and go a little bit more in depth. The first is private citizen sharing. And so I've mentioned this already, that you can use companies or private citizens. And the results that I found was that first, there's just little use of the sharing economy in evacuation. So that's just one of the first things. The second part, though, is that despite this little use, private citizens are somewhat willing to share their homes, but much more willing to share transportation, as we see in this table. We said that there's people who are extremely willing to share in a future disaster. We see that for wildfires, it's much higher than hurricanes, and transportation is much higher than sheltering. And what's also an interesting part, and the hypothesis behind that, is that transportation is somewhat temporary. They may not have to be in your vehicle for that long, maybe half an hour, maybe an hour. If it's a hurricane evacuation, maybe much longer, but that's maybe the difference in willingness. But what is also good is that I found that there's capacity in spare beds or mattresses, as well as spare vehicle space for a person and their belongings. And so this really indicates that there is capacity, that there is willingness to provide resources. The question now is, how do we match that demand with the supply? And some of my recommendations that come out from this work is, first, we need to bolster neighborhood and community networks. Because private citizens are so willing to provide this sharing, perhaps it's through neighborhoods and community networks. But this type of approach will require training and perhaps even integration into current mechanisms, such as community emergency response teams, also known as CERTs. And so that's just a cautionary message that a lot of pre-planning is going to have to come into play if we're going to actually leverage these types of resources. Now, in terms of influencers on sharing, I found a number of different important factors that influence this willingness. For wildfires, what's most important is trust and compassion. If people trust other people, either strangers or neighbors, or they have compassion for other people, this increases willingness regardless of either wildfire data set or regardless of resource. And so these are really critical factors that influence willingness. Other factors that increase willingness include past disaster volunteers, members of community organizations such as PTAs or political organizations or labor organizations, professional ones, sports clubs even. And then also what's an interesting part is evacuation urgency. And the hypothesis is that there is some triggering mechanism that once you're in the evacuation situation and it's really bad, for example, high visual fire level, people may realize that their neighbor's only option of being able to get out is through them. And therefore, they are more willing to share resources at that point in time. For both hazards, unfortunately, most demographic variables were pretty weak or sporadic. There was no clear indication, which then kind of points back to this trust and compassion piece. However, families were unwilling to share regardless of resource, regardless of scenario, and regardless of hazard. So that's one big thing. And home sharing users were more likely to share shelter. The other result is that sharing behavior for hurricanes is definitely correlated and is linked via classes of individuals and or joint behavioral preferences. And so the story behind that is that because someone's willing to provide transportation, they are also willing to provide shelter. And so the key recommendation out of that one specifically is that we need a holistic share economy strategy. We shouldn't just focus on transportation. We should also include sheltering, and it should be across all temporal points of the disaster. Because if someone's willing to share at one point, they're likely to share at another point. And then, of course, we need to increase trust and compassion in communities if we're going to increase this willingness to share. So these next two slides are really connected. They're actually joint connected to each other. First is joint choices in hurricanes. The takeaway here is that these choices are correlated. Departure time, route choice, mode choice, shelter type, all these different choices, they are correlated, and they need to be modeled jointly to account for this correlation. And so this is a very simple table of some of the joint preferences, which is positive, and joint dislikes, which is negative. And so I want to look at the positive ones here, is that we see for early, people who evacuate early also have a preference for evacuating at night. So it's a joint preference for those two dimensions of the overall, all these different evacuation choices. Same thing with early and highway at a regular time in highway, which is a little bit, that was a label that we used for 2 to 3 days before landfall. As well as within county and multiple vehicle evacuations, and within county and within Florida and multiple vehicle evacuations. And so the story behind this is that resources need to be placed, transportation resources need to be placed for significant nighttime traffic along highways and also well before landfall. And this is a complete change from what agencies normally do. They provide that transportation response during the day, still along highways, which is good, but also during a more 2 to 3 days before landfall. So they're actually missing a lot of evacuees who may need additional transportation resources, such as Counterflow, to improve that congestion and help them along. And also to improving traffic will hopefully help for the next time around for a disaster and encourage people to still evacuate for the next one. Also, the results show that there need to be transportation resources for multi-vehicle evacuations within county and also within Florida. So there's going to be highly localized congestion in these more condensed areas. For wildfires, the same thing occurs. The evacuations are correlated and should be modeled jointly, so that's good to know. The impacts are a little not as clear, but one thing I do want to note is the night and within county. This was positive, a joint preference for both wildfires, which is why it's bolded. And the story behind this is that resources need to be available for highly localized congestion during the night, but also for at the height of the wildfires, which is talked about here as immediate. So this is extremely important, because if we are looking for hurricanes for best practices, we would assume we need to place our transportation resources on highways or large roads. But here, we need to focus here on local and arterial streets during the immediate breakout. And that's a big switch, but that also means that city and county governments are going to have to be the primary responder here rather than state DOTs, which happens often in hurricane evacuations. So this is a really important result, specifically for California. And then finally, I want to go over regret minimization. The unfortunate part about this, when this comes across through dissertations and research, is that the RRM models unfortunately failed to outperform the traditional RUM models, random utility maximization models, across wildfire choices. The good news is some of them performed equally well, but some also performed worse, so that was not as good. The one bright spot is that there were some weak attribute level regret, specifically at specific attributes, which would be, for example, visual fire level or the fire danger on a route for the routing choice. And I also found weak classes of regret minimizing evacuees for route and mode. Now, looking back at this specific paper, as well as this contribution, I found that there was a significant number of limitations regarding the methodology. We had single data points, which led to low sample size. There was opt-out of choices, which is, as you probably know, in revealed preference, a huge challenge. The survey was set up where someone would provide what choice they made in the evacuation, such as I departed at 5 a.m. And then they provided the attributes for that considered choice. Now, in order to calculate random regret minimization, we actually need 3 choices, 1, 2, and 3. Now, people decided not to give us more considered choices, which was aggravating, and therefore we couldn't go through and calculate the models. And we also had attribute level opt-out as well. And the other issue was low attribute level variation, which means that the difference between 5 a.m. and 5:05 a.m., which may have been the choice set of the individual that the person was considering, doesn't have much difference. It's almost identical. So it's really hard to calculate if regret occurred in that low attribute level variation world. So the conclusions, unfortunately, here are not as much policy related, but more about methodology. That we need to be improving the RP methodology to reduce considered choice and attribute opt-out, and that there should be some SP experiment just to see if regret is even viable for evacuations, but specifically give it to people who either have had experience, such as evacuees, and then also perhaps to compare it to the general population. And so those are some of the key results there. So finally, last key takeaways, these are the broad strokes. There is feasibility of the sharing economy, but substantial pre-planning is definitely needed here to overcome a lot of those different limitations that exist in the sharing economy. The good news is that the private citizen side looks more feasible than companies, but it should be noted that companies do employ workers and hosts who may also have to evacuate. And so they also have a set of choices that they have to go through. And it's important to note that in the also limitations of the sharing economy. The next key takeaway is there is joint choice making in evacuations, and we need to stop building these specific models that don't consider them at once. And the good news is that these types of models also provide specific and detailed transportation responses that were unknown to agencies before this. And then, of course, additional exploration is definitely needed on alternative decision rules, such as regret, and also further on discrete choice models, especially considering that your choice, and this is unsurprising, your choice of discrete choice model definitely impacts your results that you get out of it. The good news is that the results from a lot of my work here and some of the work I presented here can be used by practice by agencies. And so given the fact that most emergency management and transportation agencies do not facilitate evacuations using evidence-based research, this is hopefully a good step in the right direction. And then, of course, this is a building block for research, and more is needed across all those innovative opportunities, as well as focusing additionally on particularly the social equity side. So with that, I am pretty much done. I have a couple acknowledgements. My funding sources, NSF, Dwight D. Eisenhower, UCITS, TSRC. I want to provide acknowledgement to the agencies and community organizations that distributed my surveys, and the participants in expert interviews and focus groups. Of course, my primary advisors, Susan Shaheen and Joan Walker, as well as my advisors at TU Delft, Casper Korus and Adam Pell. My other committee members, Karen Trappenberg-Frick and Mark Hansen, as well as co-authors on some of these papers, which include Jacqueline Broder, Ming-Chao Yu, and Anu Kanchuria. And then, of course, my colleagues in support in the PhD program. I could not have done this without them. And so many mentors and support from many other universities for encouraging me and for helping me throughout this entire process has been really important. So with that, I'm happy to take questions or also take questions via email. But that's it for me. Thanks. All right, any questions out there? If not, or even for you, Lynn.
So Stephen, I have a question for you.
Oh, great.
All right, well, it's not going to be so shocking, right? It's something you have been talking a lot about. So we're barreling into potentially another wildfire season. Mm-hmm. So how do you think this is going to work in a recovery situation with the pandemic, and how might our study findings help us to prepare the state?
Mm-hmm. Mm-hmm. So I think there's multiple aspects to this. Obviously, the concern of compounding disasters, in the fact that evacuations are completely antagonistic, and I call it dueling. It's a dueling process. They don't want to, it's completely different shelter in place versus evacuations. And so I think there's many different considerations we need to make. I think the first is transportation, and transit-based evacuation plans are going to have to be changed to reduce capacity in transit vehicles, which may mean more buses. It may mean more runs to get people to and from shelters. And speaking of shelters, that's a whole extra piece of that, is we're going to have to think about reimagining the idea of public shelters. And I think one benefit of the work that we've done here is that we've shown that private citizens are willing to provide their resources, whether it's transportation or sheltering, and that reduces the number of people you're contacting with, which could hopefully reduce the spread of COVID-19. And so, you know, the idea of using TNCs rather than transportation network companies, rather than a bus to evacuate people in low congestion times, could be very beneficial because you're not interacting with as many people. And so this could be, and it also provides point-to-point service, which reduces your contact. The City of New Orleans City Assisted Evacuation Plan calls for 17 pickup locations that then shuttle them to an indoor arena where there's registration and processing, and then they get bused to a different shelter somewhere else, perhaps in the state, either federal or state. So the number of times people are contacting people is going to be really problematic. And so I think the share economy side can be a real benefit as we go into wildfire season. And there's, of course, a number of different other considerations that need to be made. But those are the ones that come to mind most clearly in the work that we've done here.
Do you think that the disaster preparedness sector is ready for these dueling scenarios?
No, I mean, the problem, I mean, I think there's multiple problems. First, they are challenged in preparing for these disasters to begin with. Wildfires, and especially wildfires and PSPS events, public safety power shutoff events. For those who are in California, it's when they are shutting down the power. That on top of COVID, on top of a wildfire, is really a problem, and agencies are not prepared for that in the first place. And most of their resources are going to COVID-19 response. And so they don't have time or budget or resources to devote to actually developing plans for evacuations. And even, you know, the research from 2 years ago, 26% of the 50 largest cities don't have anything to assist vulnerable groups. And I don't know the numbers for city and county governments, but I'm very, very confident that it's much worse. And so they are not prepared right now, and I think this work can hopefully assist them because it's very practice oriented and it's ready to be applied right now.
Thank you.
Sure thing. So if there's no more questions, Amanda, do you have anything that you have to end this and everything?
No, but thank you all for coming. This has been a wonderful respite in our stay-at-home orders, being able to come together over Zoom and chat and listen to these great speakers. So thank you, Stephen, and thank you, Yulin, so much for presenting, because I know you have a lot of other things that you guys have to do.
Like a dissertation.
Yeah, some little things. So, and just one last call. Any questions for Yulin?
No, I'm fine. Thanks.
Love it. Okay. Well, thank you everyone for attending, and we hope to see you guys soon.
Great. Thank you so much.
All right. Thank you.